Welcome back. Today we're going to talk about factoring. Factoring is probably maybe the toughest skill that you got to learn in algebra. But with the table puzzles method that we've been looking at the last couple days, factoring is really not too much different. It's just a very specific type of table puzzle where all you know is the answer, and you need to figure out what was the original two factors that multiplied up to give us this. If you haven't watched either the multiplication by tables method video or the table puzzles video, a lot of what we talk about in this video depends on having some background knowledge of that, so it might be worth looking at those videos again. But specifically, solving these sorts of things takes advantage of two of those properties significantly, and that is that the diagonals add up to give us our answer. So this x squared came from this box, and these 25x's came from this diagonal, and this 150 comes from this box. And takes also advantage of the cross-multiplying property, that this diagonal and this diagonal have to multiply to the same thing. Now that's kind of key, otherwise we really can't make any progress in these problems. So in almost every case, when you're factoring a trinomial like this, you end up having to solve this kind of little mini puzzle in the middle of having to think of two numbers that multiply up to something and add up to something. So I often will write when I have to factor something, or I'll think about it like this. I got to find two numbers that multiply up to something and two numbers that add up to something. So let's look at this one and proceed. So I can immediately fill in this. This is x squared, and I could fill in 150. And I might even be able to write x and x here, because it's the only combination of things that could multiply up to x squared that makes any sense. So if you want to, you can do that. I usually don't. I want to wait for a little bit and figure out what for sure do these things have to be. These boxes have to add up to 25x's, but there's a lot of combinations of things that add up to 25x's. You could have maybe 0x's and 25. You could have 1x and 24x, or 2x and 23x, and even some combinations that are some positive and some negative, like 60x's and negative 35x's. That adds up to 25x's, or 1000x's and negative 975x's. So which of those combinations do I want to write in here so that I can factor out what the outsides must be? I'm kind of stuck, except for the fact that I also know this diagonal, and so this diagonal multiplies to 150, and so this diagonal also has to multiply to 150. So I got to figure out some combinations of numbers that multiply up to 150 that also add up to 25. Now there's a lot less combinations of numbers that multiply to 150 than there are that add up to 25. And so I usually focus my attention on that times 150 number. I will often write off to the side 1 times 150, 2 times 75, and kind of work through each of these. 3 times 50, 4 does not work, I don't think. 5 times 30 does. 6 times 25, 7, 8, 9 don't divide nicely, but 10 and 15 do. And then the next combination I find is 15 and 10 again. So this is it. These are the combinations. And of these 6 combinations, 10 and 15 is what adds up to 25x's. So that's what I'm going to write here. 10x's and 15x's. So now that I know all the work, it's just a quick factoring out to figure out what the outsides have to be. These both have an x in common, and so this has to be an x, this has to be a 15, and this has to be a 10. And so this answer factors to x plus 15 and x plus 10. So this here is, of course, the what you ought to write down as a final answer. The table is just one way of coming up with that. In fact, not every textbook or teacher will teach the table. Some people will just have you write this and try to reason out what these various four things have to be. And that's not too hard for problems that don't have a number in front of x squared. But for this example, I find that the table is extremely helpful. It's quite difficult to try to solve it without, or try to factor it without a table. So let's write in here again 2x squared, and this term is negative 24. And then what goes in these two boxes will be some x's that have to add up to 8x. That have to add up to 2x. I kind of flipped and gave away part of the answer here. Sorry, guys. They have to add up to 2x's, and they have to multiply to what this diagonal multiplies to. Be careful. We don't want to come up with combinations that multiply to negative 24. We want to find combinations that come up to, that multiply up to negative 48, because 2 times 24 is 48. So if I write down all those combinations, I've got 1 and 48, 2 and negative 24, 3 and negative 16. These are all adding up to numbers that are bigger than 2. So how about 4 and negative 12? No. 5 doesn't divide 48 nicely. 6 does. 6 and negative 8. And 8 and negative 6. And that combination adds up to 2. And so that combination is what goes in these two blanks. So I'm going to write 8 x's in one of these and negative 6 x's in the other. Students will often ask, does it matter? Do I write 8 x's here and negative 6 there, or negative 6, or 8 here and negative 6 there? It doesn't matter. You'll get the same things around the outsides, just in a different order. So feel free to write it either way. Now we can factor this. This is kind of a strange example. It actually has two different answers. The answer that I usually come up with is by looking at the top row here and seeing this top row, what does it have in common, and pulling that out. They have a 2x in common, and so they're both divisible by 2 and both divisible by x. When we pull that out, then this has to be x. And if that's x, this has to be negative 6. And if that's negative 6, this has to be negative 4. Now, there is another possible factorization that can be done. If you didn't pull out the whole greatest common factor, maybe you just pulled out an x. And let me do this in a different color. Suppose if I look at these two and all I saw was that they had an x in common, then this would have to be the 2x. And if that's a 2x, this has to be a negative 3. And negative 3, this would have to be a positive 8. 8 times negative 3 is negative 24. And so, and the 8 and x adds up, or multiplies to 8x. And so, as you can see here, I really have two different answers. 2x plus 8 times x minus 3 is one possible answer. And the original answer I had was 2x minus 6 times x minus 4. Both of those, if you were to multiply them all out, will give us 2x squared plus 2x minus 24. So I got two other examples I'll show you, but if you're kind of understanding it, well, there's nothing new in the rest of this. It's just a few more examples, one with really big numbers. I will show you a trick that you can use your calculator for, so maybe you want to watch this next example for that. But here I've got 6x squared is in this corner, and in this corner I've got 90, and so that multiplies up to 540. 540 is huge, and so if I were to come up with all sorts of combinations of numbers that multiply up to 540, eventually I need to find the combination that adds up to negative 48. Because this number is so big, rather than writing all those numbers down, maybe I'll take advantage of the table in our TI-83s. So if I bring up my calculator here, if you were to turn it on and go to the y equals screen, there's a bigger factorization I did earlier. Type in the y equals screen the multiplier, so that's 540, and then divide by x. And instead of graphing this, if you hit second graph, it'll give you a table of a whole bunch of different numbers. My apologies, from my last example I was really far down in this table. In fact, forget that, let's go to table settings, second window, and then I can jump straight to starting at 1. Now I can go back to the second table and look at my graph. So here's a table of all the combinations of numbers that multiply up to 540. So notice this first combination, 1 and 540, adds up to 541. And the next combination, 2 and 270, adds up to 272. And 3, this is 183, and so forth. It's going to take me a while before I find 48. Wait a minute, I don't even want to find 48. I want to find negative 48. There's a complication that's a little strange. But for every pair of numbers here that is positive, there's also combinations that are negative. Negative 1 times negative 540, and that adds up to negative 541, and so forth. And if I were to scroll through this list, eventually, here, this is it, negative 18 and negative 30. That adds up to negative 48. And so that's what goes in the opposite corners. Negative 18x's, I'll put in one corner. And negative 30x's in this corner. And the last one had 2 possible answers. This one actually has 4 possible factorizations, depending on what we pull out first. I usually pull out the greatest common factor, so I would pull out a 6x, but you could also pull out maybe a 3x, or 2x, or just a plain old x, and get 4 other possible answers. So if this is 6x, then this would just be x, and this would have to be negative 18, and this would have to be 6 times 5 is 30, but it's negative, so it must be a negative 5. So negative 5 times negative 18 is 90. So in a different color, maybe I pull out just a plain old, well, maybe I saw 3x instead of 6x. I knew they were both divisible by 3. Then this has to be 2x's. If that's 2x's, this has to be negative 9, and this would have to be negative 10. And if I pulled out 2x's instead, I'd get a 3rd factorization, and if I just pulled out an x, I would get a 4th factorization. So, kind of interesting. One problem has 4 different answers, but then again, when we deal with numbers, some numbers have only 1 factorization. We call them prime. Other numbers, like 540, have a lot of factorizations. So, same sort of thing can happen with polynomials. The last example is kind of an easy one, except for there's this trick. There's no x's, so that makes it confusing at first. I can put in my x squared here, and I can put in minus 49 there, and to continue, I got to find 2 terms that multiply to negative 49, and they have to cancel themselves out. So one has to be positive and one negative, probably. Looking at all the combinations, there's not that many. 1 and negative 49, 7 and negative 7, or 49 and negative 1. This is the combination that cancels themselves out. So 7x's, negative 7x's, and this is x minus 7 times x plus 7. So thanks for watching. Tune back next week as we use the skill of factoring to help us solve equations.